In this video, I'm going to take you through the traditional proof of why the square root of 2 is irrational. And then I'm going to tweak it slightly to show why the square root of 7 is irrational. And then we're going to look very closely at why you can't then tweak that to show that the square root of 9, for example, is irrational, even though it looks like you can. And actually the bulk of the length of this video is going to be made up of that exploration and going quite deep into why it doesn't work for the square root of 9. Okay, here goes. To prove by contradiction that the square root of 2 is irrational, you start by assuming the opposite, that it is in fact rational, i.e. that it can be written as a over b. And crucially, we have to acknowledge that a over b is a fraction in its simplest terms, i.e. that a and b have no common factors. Which is fine. If it's not in its simplest terms, then we just cancel it down until it is in its simplest terms. And then we're still at this point, so then we continue. Okay, we're going to square both sides of our assumption here. So 2 therefore equals a squared over b squared. I'm then going to move the b squared upstairs, so times both sides of the equation by b squared. And we have this. Now, this is saying a squared is 2 times b squared, and therefore a squared must be even. Simple as that. So we deduce that a squared is even, or a multiple of 2. Well, if a squared is a multiple of 2, think of all the square numbers that you can that are multiples of 2, and you'll probably spot that, therefore, the square root of that, a, is also a multiple of 2. Well, if a is a multiple of 2, then a can be written or expressed as 2 times something else, let's say 2k. We're then going to feed that result back into our blue kind of stream of working here. So instead of a squared, we're going to write 2k squared. We're going to expand those brackets. And then we're going to cancel the 2 out from both sides of the equation. And now we have that b squared can be written as 2 times a thing. So now, in fact, b squared must also be even. Great, so over here we deduce that b squared is even, or a multiple of 2. And by the same reasoning as before, therefore b must also be a multiple of 2. Well, look, we have a as a multiple of 2, and we have b is a multiple of 2. So guess what we can do with our fraction? We can cancel it down. But we assumed right at the beginning that a and b had no common factors, and that fraction can't be cancelled down, so we have a contradiction. And just to explain that contradiction, don't just stop at contradiction. It's good to say what we assumed and why that doesn't work. So we assumed that the square root of 2 could be written as a over b, where a and b had no common factors. And this logically then led us to deduce that a and b in fact share a common factor of 2. Well, that's clearly a contradiction, and therefore the assumption we made at the beginning is wrong, and square root of 2 is in fact therefore irrational. And that's it. And if you wrote that out in an exam, if the question was to prove that the square root of 2 is irrational by contradiction, then you just write all of that out and you get probably 4 or 5 marks, and you're done. And what they might do in the exam is give you something that looks like this proof and ask you to find the mistake in it. And obviously you have to know this proof pretty well in order to find the mistake. So it's good to just learn this and write it out a few times. Okay, let's look at the square root of 7 then. Well, let's just look through and think where we've written 2, we should just be able to write 7, and let's just see if it works. So starting up here, assume the square root of 7 is rational, so that root of 7 can be written a over b, where a and b have no common factors again. So therefore 7, if we square both sides of that equation, 7 equals a squared over b squared. Times both sides by b squared, we have 7b squared equals a squared. And that tells us that a squared is a multiple of 7 for the same reasons as before with 2. And therefore, if a squared is a multiple of 7, then a must be a multiple of 7 too. And therefore a can be expressed as 7k. If we replace our a in here with 7... I'm doing it in the wrong order. 7k. And we multiply out the brackets. We've got 49k squared there. Then we can cancel out a factor of 7. And we have b squared equals 7k squared. Which leads us to deduce that b squared is in fact a multiple of 7. And therefore b is a multiple of 7 too. We've got a contradiction because both a and b are multiples of 7, which goes against our statement up here about having no common factors. And then we can complete or correct our conclusion at the bottom. So we assume that the square root of 7 equals a over b, where a and b have no common factors. And this led us to deduce that they in fact share a common factor of 7. Therefore, the assumption is wrong. Root 7 is irrational. Anything wrong with that? Absolutely not. It's perfect. That is absolutely fine. You can do that. It works. No logical problems with that. So it begs the question, where is the problem if we change all the 7s to 9s? Let's just do that a moment. Let's start, well first let's just rub out all of the 7s. So we've now got a completely kind of blank template for one of these proofs. And let's start filling in some 9s. Right, I'm going to pause at this point. So I've just got to this point here, where we've found that a squared is a multiple of 9. Does this therefore mean that a is a multiple of 9 too? And the answer is, it does not. Why not though? This is the problem. This is where the problem is with this proof for the square root of 9. And actually, if you carry on, now you shouldn't carry on because we've made a logical fault, but if you carry on, you actually get the same problem arising here as well. So both of those deductions are wrong. That symbol there is wrong because the line above it, a squared is a multiple of 9, does not imply that a is a multiple of 9. Well, why not? Let's look into that a little bit more deeply. So throughout everything we're doing from now on, we're going to let a always be a positive integer. Also, I haven't written here that we're going to let p comes up in a little bit later, p is going to be a prime number. So whenever you see p, it's prime, and a is a positive integer. So the first thing we want to do is disprove this claim that if a squared is a multiple of 9, then a is a multiple of 9. Well, disproof is generally straightforward. It's not always straightforward. I mean, take the Riemann hypothesis, for example. People have been trying to disprove that for years and got nowhere. Hasn't been proved either, of course. But disproof that you'll come across in A-level is generally quite straightforward because all you need to do is find a counter example. Find an example of it not working, and therefore it's simply not true. So, well, let's look at some examples of where it works. If a squared is 81, which is a multiple of 9, then a is 9. Great. It works there, both multiples of 9. If a squared is 324, then a is 18. That seems to still work. But we don't have to look very hard to find a couple of counterexamples. If a squared is 9, that's clearly a multiple of 9. Then a is 3, which isn't a multiple of 9. And it also works for 36. Square root of which is 6, which is obviously not a multiple of 9, even though 36 is. So we've got two counterexamples here. We only needed one, but we've got two. Contradiction. Counterexample, rather. So it's disproved. If a squared is a multiple of 9, then a is not necessarily a multiple of 9. So it's straight there. We're looking at it now. That's the reason why the proof on the previous page didn't work. But let's go deeper. Why does it work for the prime numbers 2 and 7 that we looked at? And would it work for any other numbers that are not prime? So here's the conjecture, if a squared is a multiple of 7, then a is a multiple of 7. Now what you're about to see isn't a proof of this, it's just us trying to convince ourselves, which is different from a formal proof. I do something closer to the formal proof in a minute, in a slightly more general case, on the next page. But let's just convince ourselves why it works for 7, where it clearly didn't work for 9 in the green text on the page you're looking at. Well, look, it works for 49. This isn't part of the proof, remember, this is just looking for examples. You'll never ever get marks for just looking for examples of something working in A-level, because it doesn't mean anything. It's only an example where it doesn't work is in fact a proof. It's a counterexample disproof. But here let's just convince ourselves it does in fact work for 7. Here's a couple of examples of it working. Now, you could go on and look for more, but I can tell you now that they will always work. You'll always get A as a multiple of 7. Why does it work? Okay, let's think of just some number and call it A. Here we go, there's a number. Now I don't know what that is, I haven't actually multiplied those together and found out what the answer is expressed as a conventional number. But there is a letter A, or number A, written as a product of its prime factors. Now, clearly that number is divisible by 2, 3, 7 and 11. What happens when we square it? I know we're going the wrong way here. We're starting with A and getting A squared, and we're supposed to go the other way. But let's just see what happens. Well, we had 1, 2 in our prime factorisation before, so we're going to end up with 2 2's here. We had a 3, now we're going to get 2 3's. We had 2 7's, and we're going to get double that many. So we're going to have 4 7's, and of course we'll have 2 11's as well. So in this number A squared, a square number of course, we have even powers on all of the prime factors. Of course we're going to get even powers on them all because we've doubled the powers on the prime factors in some already existing number A. To get an A squared, we have to double them all, and therefore we'll have even prime factors. Well, for looking at what we can see there, if A squared is a multiple of 2, then A is a multiple of 2. We can see that very clearly. If we look this other way, this number is a multiple of 2, there's a 2, and therefore, as we can clearly see, A is also a multiple of 2, it's got one there. And the same is going to work for 3, and the same is going to work for 7, and the same is going to work for 11. But does the same work for anything else? Because look, A squared is a multiple of 9. Look, there's 3 3 there. 3 squared. 3 times 3. But look, A isn't a multiple of 9. It's only got 1 3. It needs 2. It needs at least 2 to be a multiple of 9. So if A squared is a multiple of 9, then it does not imply that A is a multiple of 9. Sorry. It works for all the prime numbers because they only have to appear once in the original A. 1 2, 1 3, at least 1 7, 1 11. But it doesn't work for 9 because we need 2 3's, or at least 2 3's in the original number. And when we halve this even power, we lose the fact that we had at least 2 3's. So it doesn't work for 9. So hopefully looking at that, you're convinced that this will always work for prime numbers, but it will not work for a square number. But what about numbers that are neither prime nor square? For example, 6 or 12. Well, what is 6 really? Do we actually need the number 6? No, we don't really, do we? We could always just use 2 and 3. If somebody says, is this number divisible by 6? You could say, well, what you're really asking me there is the number divisible by 2 and is the number divisible by 3? Because if it's divisible by both, then it's divisible by 6. Well, let's look and see if this works for 6. Is A squared divisible by 6? Yes, there's a 2 and a 3 there. Is A divisible by 6? Yes, there's a 2 and a 3 there. So it seems to work for 6. But that makes sense, doesn't it? Because asking whether it works for 6 is really just looking at these two lines here. Does it work for 6 is saying, does it work for 3 and does it work for 2? And the answer to both of those is yes, and therefore it works for 6. Does it work for 12? Well, 12 is, again, we don't really need the number 12. We just need 2, 2 and 3. 2 times 2 times 3. That is the number 12. Well, is a squared a multiple of 12? Yes, it's got a 2, and a 3. But is a multiple of 12? No, it's only got 1, 2 and a 3. So it doesn't work for 12. Why doesn't it work for 12? Because we're really asking, does it work for the square number 4? And does it work for 3? Well, we know it works for 3 there. But as we've deduced, it's not going to work for quite a lot of square numbers, necessarily. It actually does work for some... in this particular example, it does work for the square number 49 squared. This is 49 squared. And if a squared is a multiple of 49 squared, then... if a squared is a multiple of 49, then a is a multiple of 49 as well, in this particular case. But you can imagine if that wasn't 7 to the power 4 and 7 to the power 2, but in fact 7 to the power 2 and 7 to the power 1, it wouldn't work. We'd have 49 here and only 7 here, so it wouldn't work. So again, if you've got... 12 doesn't work because you've got square number 2 squared and 3 as prime factors of it. If I'm starting to lose you here, don't worry too much about that. The fact is, this idea works for primes, and it works for simple products of primes, but it doesn't work where you've got a repeated prime. For example, 3 squared here, or in the number 12, you've got 2 squared buried in there as well. Anyway, let's press on. We're going to look at slightly more formal proof now of if a squared is a multiple of a prime, then a is a multiple of that prime. Now, logically, you can use this bit of kind of logic theory here. This is a little bit beyond what you'd be expected to do in A level, but it's part of the picture here. If you can understand this, then it would be great for your general understanding of proof. So here's a bit of logic theory, starting with this idea here. If A implies B, then B complement implies A complement. An example of this is, if it's raining, then I will take an umbrella. And therefore, logically, if I do not take an umbrella with me, it is because it is not raining. Well, if you're therefore trying to prove that A implies B by contradiction, the trick, firstly, is to note that it is sufficient to prove that B complement implies A complement, just using this statement up here. That's accepted logic theory. So if you're trying to prove that A implies B, then it's sufficient to prove that B complement implies A complement. We then assume the opposite of this, i.e. that B complement implies A instead of A complement. Part 3 is to basically, with the algebra or whatever you're faced with, try and show that that leads you to a contradiction. And part 4 is just to make a conclusion that B complement implies A complement, which is the opposite of our assumption. Our assumption is that one. And therefore, if B complement implies A complement, then A implies B. So that is the sort of process for a proof by contradiction that A implies B. So now applying this to our statement at the top, I'm going to make these two statements, two definitions of A and B. Sorry, I've whizzed on a little bit there. Let's come back. So my A and my B are those. I'm trying to show that A implies B. Well, we're going to assume that B complement implies A, which is this step here. i.e., we want to show that if A is not a multiple of P, then A squared is a multiple of P. That's B complement implies A, written in context. Well, concentrate carefully here. We're going to let a be this number here, a little bit like the prime factor idea from the previous page. I'm just going to write this out then explain it. What we've got here is we're defining an a to be p to the power 0, and then we've got all these other primes here. So I should have written this. If this was a formal proof, I'd have written let p, q, r, s and t be primes. And I've put this ... here to say there are maybe other primes as well in this definition of a. And we've got the powers on those primes in the prime factorisation of a. And I've deliberately written p to the power 0 to say it does not have a p. It's not a multiple of p. We need it not to be a multiple of p. Now, if we square a, we're going to double all of the powers on those primes. So double 0 is 0, double w is 2w, and r to the 2x, s to the 2y, t to the 2z, ... So all we've done is double all of the powers here to get these powers here. Now we can see very clearly there that if a is not a multiple of p, then a squared is also not a multiple of p either. So we've gone against our assumption. This is a contradiction. If a is not a multiple of p, then a squared is clearly not a multiple of p either, and therefore b complement implies a complement, and therefore a implies b. So you have a relatively formal proof there that this works in those cases of 2 and 7, etc. So going all the way back to the beginning here, to the square root of 2 being irrational, this proof, it was this step here that we kind of glossed over when we did this the first time, but you've now seen actually how deep the rabbit hole goes there. If a squared is a multiple of something, stating therefore that a is a multiple of that thing really requires this number here to be a prime number or a simple product of prime numbers where we haven't repeated any of those prime numbers. So remember, it worked for 6 because that was just 2 times 3, but it didn't work for 12 because that was 2 times 2 times 3. So this whole proof that you're looking at here hinges on the fact that that number there needs to be really just a prime number or a simple product of primes such as 2 times 3 or 6. Now, just before I finish, I will mention that you might be thinking then, surely we showed that this worked for root 2, it worked for root 7, it didn't work for root 9 because of this problem here. But it sounds like I'm saying that it would also fail for root 12. But root 12 is irrational. So how would you prove that, by contradiction perhaps, that the square root of 12 was irrational? Well, simply, you just write the square root of 12 as 2 root 3. And then the whole problem just comes down to showing that the square root of 3 is irrational, using this proof that you're looking at in front of you. Just change all the 2's to 3's. And of course, if the square root of 3 is irrational, then twice the square root of 3 is also irrational. And of course, twice the square root of 3 is root 12. Any questions, drop me an email, come and see me, and I'll try and explain. Thanks for listening.